In this video, I'm going to present how to remove the pulse artifact or so-called ballistocardiogram artifact from the EEG data registered during simultaneous EEG-fMRI recording. The presented procedure is part of the EEG-fMRI data processing pipeline described on the BESA wiki. In a previous BESA YouTube video, I showed how to remove the fMRI gradient artifact. Please refer to it if you do not know how to remove this signal distortion. As a first step, I recommend to filter the data using the artifact frequency range. The pulse artifact typically has a frequency between 1 and 20 Hz. To change filter settings, press the EDF button. Switch on the low cutoff filter and change the value to 1 Hz. Switch on the high cutoff filter and change the value to 20 Hz. I will also adjust the slope to 12 decibels in octave. Press OK to apply the filter. Now the artifact is much more visible. In the next step, I will change the search tool behavior from search average right to search average view. This has to be done only once. To do so, go to the search menu and check Search Average View. Note that the fourth button in the control ribbon changed from SAW to SAV. Now I will mark the part of the signal where the pulse artifact is clearly visible by dragging the mouse over it. When I press the SAV button, a new pop-up window is displayed. Some settings should be adjusted here. I will use all channels for searching. Obviously, I want to use current filters and current buffer width. The threshold settings can be left with default values. Optionally, an SNR detection threshold value can be applied. I do not need any additional options. When I press OK, the automatic search procedure starts. Once the searching process is finished, an averaged buffer will be shown on the left part of the screen. This buffer contains the average of all detected artifacts. As a good practice, check if artifacts were detected across the whole time range of the fMRI session on the event ribbon. Note that not all artifacts have to be detected. The places where artifacts were not detected will be corrected anyways. Now I mark the whole buffer by clicking the right mouse button within the buffer area and selecting whole segment. The buffer is now highlighted in yellow. Now I press the right mouse button again over the yellow shaded area and select Define Artifact Topography. An artifact topography definition window pops up. I tick the EKG checkbox to assign the artifact topography. The artifact topography is obtained by computing a principal component analysis, PCA, over the selected area. Note that an artifact topography map is also displayed on the right. You can switch between components using the vertical arrows in the mapping window. Now I need to select the number of components for spatial filtering. In the drop-down list, the first value is the number of components used, and the number in brackets is the variance explained by the last component. I recommend using all components that explain more than 1% of artifact variance. A warning message is displayed informing that using too many components may distort your data. You should not use more than 3 components unless you are dealing with simultaneous EEG-fMRI recording where artifacts are very strong. Now I will switch to the Estimates Signal tab, where settings of brain signal estimation can be changed. By default, the adaptive method is selected. This is the recommended setting for continuous data. Now I press OK to close the dialog. Note that we do not see the pulse artifact anymore. even in places where artifacts were not detected by the pattern search. From now on, further processing can be performed like for regular EEG data registered outside of the MRI bore. As an example, I will present a simple ERP averaging process. First, let me press the ERP button. Then I switch to the Filter tab. Note that we can use different filter settings from the ones used during Pulse artifact template creation. Both procedures are independent. I switch to the Artifact Rejection tab. When I press the Start Scan button, the automatic artifact rejection tool will start. Please keep in mind the naming difference. Before, I performed artifact correction, which means that I tried to clean up artifact-contaminated data so it could be used for further processing. With this step, I will reject the epochs that still have some residual noise from further processing. Note that if artifact correction for fMRI gradient and pulse artifact is on, the correction procedure is taken into consideration during artifact rejection scanning. That simply means that the artifact rejection tool evaluates artifact corrected data. To check whether artifact correction is on, verify if the blue text corrected is present in the leftmost corner. Once the artifact rejection scanning is completed, I go to the Average tab and press the Average button. Since I performed the pulse artifact correction, a prompt is shown. In the dialog, I can choose whether I want to turn off or keep on artifact correction for the averaging process. Turning off the artifact correction for the averaging process reassures that no distortion to brain signal topographies will be introduced. I choose yes, so I will turn artifact correction off for the averaging process. I will turn it back on just after the averaging. I will save the file with default name and with default condition name. The file with averaged ERP data is automatically opened with top view on, which I will close for now. Now I will press the EDF button to adjust the filters to the ERP range. I will use a 0.1 Hz high-pass filter and a 20 Hz low-pass filter. I will set the slope of the low-pass filter to 24 decibels per octave. The very last step is to turn pulse artifact correction back on again. To do so, I go to the artifact menu and select Load. Now I select the ATF file that was created automatically when I corrected the pulse artifact at the beginning. By pressing Open, the artifact correction will be applied to the average data. Since for ERP analysis, the recommended brain signal estimation is a surrogate model, I will change this setting. To do so, I visit the artifact menu again and select Options. I will use a default model which can later be trimmed to the particular experiment. When I press OK, the window is closed. Note that now in the status bar the correction state is SUR, which means that the surrogate model is used. In this example, I expect to see a visible auditory N1 wave, which in fact is already visible. By double-clicking the left mouse button on the N1 wave position, I can examine what the signal sculpt distribution looks like. Two bilateral sources in the auditory cortices are clearly distinguishable. For more details about artifact filtering and EEG-fMRI data pre-processing, please refer to the BESA research tutorial document and to the BESA wiki.